Welcome back. Today we are going to look at probability. We have already looked at thermodynamics. And now we want to bridge the gap with the statistical mechanics. So now probability is nothing but common sense. We encountered this in plenty of occasions in our daily life. For example, if you toss a coin, then you know that the outcomes are random, right? So there is a certain probability of getting a head or getting a tail. Similarly, if you roll a die, let's say it's a 6-faced die, then the number that comes up is also random. So the possible outcomes are 1, 2, 3, 4, 5 and 6. So all of this tells you that nothing in nature is deterministic. So this is completely opposite of what you have encountered in Newtonian mechanics, where given a single particle, given the forces, you know that the trajectory is completely deterministic and therefore you can determine the trajectory at later times. Exactly. But here in these events that you see that the outcomes are random, right? So therefore one has to figure out a way of quantifying probability, right? So let's say, for example, if I have a box which has different balls, colored balls in it, right? Some of them can be red. So let's say 2 of them are red, 1 of them is blue, 1 of them is green, and 1 of them is black. So there are 5 balls in the box and you pick up 1 ball at a time. Then the probability that you get a red ball is 2 by 5. Probability of getting a red ball is 2 out of 5. Similarly, probability of getting a green ball is 1 of 5, and probability of getting a blue ball is also 1 of 5, and probability of getting a black ball is again 1 of 5. Right? This you are familiar with, you have already encountered this many times, right? So now we want to quantify this probability. So what is called rules of probability. Let's drop it down. So you see that for a given event, which could be like tossing a coin, rolling a die, there are outcomes. We will call these outcomes as omega I, right? So these are the elements that we normally talk about. So these outcomes make up what is called the sample space of the system. So these outcomes omega I make up the sample space S, so that we can write down omega I is equal to S. This event where you have tossed a coin is typically what is called a trial. So for tossing a coin, I know the outcomes are either head or tail, and therefore this is the sample space for this event. For rolling a die, let's be a little bit more specific, which is a 6-faced die, then the sample space are 1, 2, 3, 4, 5 and 6, and this is the sample space. So all the outcomes taken together, they form the sample space. The only so this choice of this sample space clearly depends on the event, on the type of event that you're looking at and the type of probabilistic question you are asking, right? But as a general rule, the outcomes omega I and omega j are mutually exclusive. What does this mean? This essentially means that they do not occur simultaneously. Right? This is my first. The second one that we want to also look at, that the total number of outcomes must give you the sample space. If you are missing something, then you know that this is not the sample space, which essentially means that the elements, the set of elements should be complete, which we wrote down in the earlier statement, that omega I must give you the sample space. So given these two, one can write down that the probability, you can assign this probability to these outcomes by saying that P of I must be greater than equal to 0, less than equal to 1. This is nothing but common sense, and this is what is called the positivity rule. The second quantity, the second rule that one should also define is sum of P of I must be 1. So probability of all the outcomes must be unity, and this is what is called normalization. Additivity, if A and B are mutually exclusive, which means that A intersection B is equal to phi, then probability of A union B is P of A plus P of B. One can generalize this statement also by saying that if AI and AJ, two of these outcomes, are pairwise mutually exclusive, then P of this is sum over P of AI. For example, so if AI and AJ are pairwise mutually exclusive, which means that if AI intersection AJ is the null set phi, then the additivity theorem can be generalized in this form. For example, if I roll a die and then I ask the question that what is the probability of getting a face or a number, let's say 3 or 6, then the probability of this is essentially P of 1/6, of getting a value 6, which we shall denote P6, and a probability of getting a value P3, which is 1/6 plus 1/6. So we will write down this as P of 3 or 6 is equal to 1/6, which is 1/3, right? So now what we come to is essentially the interpretation of probability. So whatever we have discussed is essentially we have quantified the rules of probability. So now we want to look at interpretation of probability, and there are mainly two interpretations that is mostly encountered. One of them is based on symmetry, and the example for this is a coin toss in which the possible outcomes are head and tail, and therefore here it's a two-state system in the sense it is a Z2 symmetry, and each of these has a probability half and half. A similar argument is, let's say, an n-faced die. In an n-faced die there are n faces, and if it's a fair die then all of these faces are equally likely to appear, so the outcomes are I equal to 1, 2 all the way up to n, and this is also your sample space, and therefore probability pi of getting a face with number I is equal to 1 by n. So this is clearly based on symmetry. The other interpretation which is also often used is the frequency interpretation. Now in the frequency interpretation, what you have is essentially you have n number of trials. So if you are tossing a coin, you toss it n number of times. Then probability of getting a head is the number of times you get a head divided by the total number of trials that you have done. Similarly, probability of getting a tail is the number of tails divided by the total number of trials. So this is typically what is called a frequency interpretation, and this is what is called a symmetry interpretation. Most often in experimental science as well as in analysis, in data analysis, this is the interpretation that you see. The frequency interpretation is the interpretation that is most often. So for any in the frequency interpretation, for any outcome A, the number of times that outcome appears divided by the total number of trials is the probability of this. So now we want to look at what is called the conditional probability. And the conditional probability, as the name suggests, is that you are asking a different question now, conditional. So the question that you are asking now, that what is the probability of an event A given that another event B has occurred. And that we denote as PAB is essentially given by PA intersection B divided by PB, right? If you want to ask a different question, that is what is the other way around, probability of B given that A has occurred, and the answer to that would be PB intersection A divided by P of A. Now both these very simple expressions have a very nice interpretation. What you are doing, since it's being conditioned on an event A, you are essentially restricting the whole sample space to the event of B, and this becomes your new sample space. To illustrate this, let's look at an Euler diagram, and let's say this is my sample space S. Let's denote the events by different colored circles. There is a green and then there is a red. It's not drawn to scale, right? So let's now put label the events. Let's say this is A, the blue one is B1, the red one is B2, and the green one is B3, right? And now we need to put numbers to it. So this is 0.3. This 0.3 does not include the area which is enclosed by the blue circle, but rather just the part over here. This is the difference with the Venn diagram. This is 0.2, this is 0.2, right? And then B1, let's call this as 0.1, and B3 also we will call it as 0.1. The first thing to note is that I have what is the total number that it should add up to unity. So 0.3 plus 0.1 is 0.4, 0.6, 0.8, 0.9, and therefore the rest of the sample space has 0.1. Now then you should note that probability of A is 0.3 plus 0.1 plus 0.2, which is 0.6. Probability of B2 is 0.4. Probability of B3 is 0.1. Now let's say you want to ask the question probability of A given that B2 has occurred, right? If you look at this very carefully, then you see that half the time B2 has happened, A has happened. So very quickly you can see that this answer is half. And if I want to use the formula that I've given over here, then A intersection B is 0.2 and the probability of B2 is 0.4, which is half, which everything agrees very nicely. A given that B1 has happened, probability of A given that B1 has happened is essentially, if you look at this Euler diagram, then you see every time B1 has happened, A1 has happened. Unlike the first case when you looked at B2. Not always when B2 has happened, A has happened. Only half the times B2 has happened, A has happened, and therefore you see this is the first probability is half, but the second probability is 1, and the answer is also, if you get back the same answer if you use the expression that is given over there. Probability of A given B3 is 0, which is very true because probability of A intersection B3 is 0. So this essentially tells you that the two expressions you have, it clearly tells you, this illustration clearly tells you that you are restricting the sample space to the sample space of B. Well, in this case B2, in this case B1, and in this case B2. So that these events B1, B2, B3, they become your new sample space when you are asking for the conditional probability P A given B1, P A given B2, P A given B3. Now let's take a formal derivation, try to see if we can formally get these ideas. So let S be a sample space, right? And if this sample space has outcomes omega, right? So that this forms the sample space. Suppose that now an event has occurred, and this event B is a subset of S, correct? Now a new probability needs to be assigned on omega with this knowledge. So we want to assign a new probability on omega. We want to assign a new probability of omega given that we know that the event B, which belongs to a subset S, or a subset of S, has happened. So if omega belongs to B, then probability of omega given that B has happened is equal to, let's say, alpha times omega, where P omega was the unconditional probability. We did not condition it on anything. And clearly if omega does not belong to B, then P of omega given B has happened is equal to 0, right? We further have the normalization condition that if this belongs to S, probability that this is equal to 1, correct? So I can now expand this. So I can write down P omega belonging to S as this one as P omega belonging to B, P omega B plus P omega belonging to B complement, or P omega not belonging to B, since we have used them, But by our conjecture, with the hypothesis that we started off with, this is 0. And therefore, I have omega belonging to B, and this quantity is alpha times P of omega. Since omega is now restricted to B, therefore this is P of B, and the left hand side is 1. So that alpha becomes very nicely P of B. And therefore, you see, for any event omega that belongs to B, you have reassigned the probabilities that P of omega, given that B has happened, is 1 of P of B times P of omega, right? Now for any general event A, let's say, for any general event A, I want to write down P of A given B, and that by definition is that omega belongs to A intersection B. So P of omega given that this event belongs to this set of A intersection B plus omega belonging to A intersection B complement, which is the rest of the sample space, but this is 0, right? So therefore I have sum over omega belonging to A intersection B, P of omega given B, which is equal to sum of omega sum of all the outcomes belonging to the set A intersection B, P of omega divided by P of B, and therefore this is 1 over P of B, P of A intersection B. So this is a very simplistic derivation of the expression that we did before. So what we essentially, again to summarize, what we essentially did was we looked at the sample space, and then we said, look, now an event has happened and I want to condition on this event. So for that purpose, I want to reassign the probabilities of the outcomes given that this event has happened, and let's say that event is B. So all we did was we said that if omega belongs to B, then this must be a renormalized probability with alpha times P omega. If omega does not belong to P, then that probability is 0. So then we use the normalization condition. If omega belongs to S, P omega given B must be equal to 1. And once you have the normalization condition, then you can expand this as either omega, the outcome, belongs to B, or the outcome does not belong to B. If the outcome doesn't belong to B, then the probability associated with is 0, right? So therefore the left hand side is 1, and that gives you the normalization. And then if you consider any event A, for any general event A, PA given B has happened is essentially P of omega, the probability of an outcome omega, probability of an outcome omega given that B has happened, such that omega belongs to A intersection B and A intersection B complement, but this probability is 0. Then this expression I can further write down. I can substitute for P omega given B, and essentially you get this nice result. As an example, so of conditional probability, let's take the following. So you know that your neighbor, let's say your neighbor has a son, right? They have 2 kids. So let's say has 2 children, right? Now given just this information, if I ask you that what is the probability that your neighbor, the children of your neighbor are both sons, he has 2 sons, then you will say, oh, that is very simple to answer. Let's look at the options that we have. Both of them are boys, one of them boy girl, girl boy, and then girl, girl. So this is the sample space that you are looking at, and you will immediately say that, look, if I do not have any other information, then the probability that both of them are boys is 1/4. Probability that both of them are boys is 1/4, equally likely to happen. But now I give you an additional information that one of them is a boy. So now you ask the question that what is the probability that the other one is also a boy? So you ask the question, what is the probability that the other child is also a boy, right? So what you are looking for is essentially, you're looking for probability of BB, right? So in this whole, when you say that one of them is a boy, then you see this sample space gets restricted to BB, BG, sorry, there's no comma here, and to GB, right? So let's call this as, both of them are boys, as F, and this one as E. Then the answer that I'm looking for, P of F given E, because this part E is essentially is the answer to this question, that if one of them is a boy, then your new sample space is just these three, right? And which is E. And the answer that you're looking for is what is the probability that the other child is also a boy, is essentially that your neighbor has two boys, is F. Let's denote them as F. Then the answer is P of F intersection E given P of E, right? So that is probability of BB divided by probability of BB, BG and GB, correct? The probability of BB is clearly 1/4, which we have worked out, and the other one is 3/4, and therefore this is 1/3, right? So this is how you essentially use evaluate conditional probabilities. It becomes very, very clear to you once you write down the questions and once you write down the sample space that you are really interested in, that the conditioning has forced you to do. So one can of course write down a frequency interpretation. Interpretation of conditional probability. And there, suppose you have n trials, right? And then essentially you count the number of times that event A has occurred, and let's denote it as NA is number of times event A has occurred, and NB is the number of times event B has occurred. And one can also have the number of times when both A and B has occurred. Right? Then if n is large enough, statistically speaking, so then P of NA, as we have P of A as we had worked out earlier, the frequency interpretation, P of B is NB over N, and P of A intersection B is N of A intersection B by N. where this denotes essentially the number of times A and B has jointly occurred. So the conditional probability in the frequency interpretation becomes n A intersection B divided by n, right? So we want to now look at what is called the partition theorem. So please realize that this material and probability is just a bridging between thermodynamics and statistical mechanics. So we are not going to do anything in detail because I'm sure you have learned probability by now in several times. So now let's look at the partition theorem. What does the partition theorem tell you? That so let the sample space be written as, right? Then essentially AI is called a partition of S. What does this mean? That means I can have this is my whole of my sample space. I can A, right? So this can be A1, this can be A2, this can be A3, A4, A5, and this can be A6. So all these A1, A2, A3, A4, A5 are events, and these are subsets of S, except that this whole thing essentially makes up the sample space S, right? If I now consider a B, which is a subset of S, and denote it over here like this way, right? Then you see there are several intersections, right? And now with this, so let's call this subset as B. I can write down B as union of right? So then if I want to calculate the probability of B, then essentially I will calculate indirectly the probability of this quantity, right? And by the additivity theorem, this is nothing but sum over I, probability of BA intersection AI, right? But then I know that essentially this is going to be sum over I, P of AI, P of B given AI, right? So this tells me that the probability of B I can write down as in this particular form, where AI is at the partition of S. Now I also know that probability of A is probability of A given B plus probability of A minus of B, that is B has not occurred. P of A intersection B is, P of conditional probability of A given that P has occurred is P of A intersection B divided by P of B. And as we had already written down, P of BA given that A has happened is P of A intersection B is divided by P of A, which means it clearly that A intersection B is, you can either write it down P of B, which is also P of B given that A has happened times the probability of A, right? Therefore, you see I can write down this P of this conditional probability, that probability of an event A given B has happened as probability of an event B given that A has happened times PA divided by PB, right? Now if there are multiple events, this is just one event I'm talking about. If let's say this A, there are multiple events AI, and I want to know P of AI given B, then P of AI given B is this just very simple expression, P of B given AI times P of AI divided by P of B. But P of B we just calculated, right? Using the partition theorem, we calculated this as sum over, we use this expression, P of AI times P of B AI. So this is the generalization of the Bayes theorem. This relation that you see over here is the Bayes theorem. Now, the advantage of this expression, the Bayes theorem that we have seen, is first of all, not only it tells us how the probability is modified with the presence of new evidence, but you see in this expression what we have done is we have written down PA given B has occurred in terms of PB given A times PA divided by PB. So we have kind of recast this calculation of this probability. Often the three quantities that you see on the right hand side of this expression is much easier to evaluate and is much easier to estimate also. So therefore this gives us a very useful expression. As an example, let's say I have a computer program, right? And this computer program has two modes. So let's say computer chess program, and this has two modes. One is an expert mode and the other one is a novice mode, right? Now the expert mode, so we will say that this is the expert mode, this is the novice mode. In the expert mode, the expert mode beats you 75% of time, right? And the novice mode will you have a 50% chance of winning. So what you do now is, let's say you close your eyes and you select a mode. You do not know which mode you have chosen, right? You randomly choose one of the modes and the computer wins both times. So you select a mode randomly and the computer wins both times, right? Now you ask the question that what is the probability that you chose the novice mode. So I want to ask the question that what is the probability that you chose the novice mode. See, if all this information was not given, which means all this information means that the computer wins both times. If this information was not given to you, then you would say that the probability of choosing a novice mode and winning twice is 1/4, right? Sorry, is 50%. So probability of choosing the novice mode and winning is 50%, right? So but now essentially what is being asked here is what is the probability that you chose the novice mode given that you have the computer has won twice. So what is the probability that you seek? Novice mode given WW, right? So W denotes a win. But this I can clearly write down WW n, I'm reversing the question now, times P of n divided by P of WW, right? By the Bayes theorem that we have written down, I am just reversing this expression. So I want to know what is the probability that I have chosen the novice mode given that the computer has won twice, and I want to rewrite this, I want to evaluate this by choosing this expression where it is expressed in terms of a different, I think, probability that you have of winning twice given that you have chosen the novice mode, right? So now probability of choosing a novice mode is half, because there are only either you choose the novice mode or you choose the expert mode, and you have closed your eyes and you have selected one option, right? And therefore probability of winning given that you have chosen the novice mode is 1/4. That is very clear, right? Now I have to figure out what is the probability of winning twice. And here essentially there are two possibilities. One is you chose novice mode and won twice. You chose expert mode and won twice. Correct? So therefore I can write down PWW as probability that you have chosen the novice mode and won twice, plus the probability that you have chosen the expert mode and won twice, right? So probability of choosing the novice mode and winning twice is probability of n times WWN. Okay, so let us write down the same thing in a different way so that it is much easier to. So probability of winning given novice mode times probability of novice mode plus probability of winning given expert mode times probability of expert mode. This we have already calculated to be 1/4. Now this is creating a slight problem, and this is half, correct? And this I know is 3/4 whole square into half. And if I add everything, let's say this is going to be 1/8 plus 9/32, which is 13/32. So now I have all the information. So now I can calculate P of n WW as PWW n Pn divided by P of WW, which is PWWN is 1/4, half, and this is 13/32. So this is going to be 4/13, which is approximately 0.31. So now you see the answer is that there's a 30% choice of you choosing the novice mode. If it has reduced from 50% to 30%, so the probability of choosing the novice mode was 50%, right? Good. So now that we have the bare bone structures of probability theory ready, we want to look at some examples of probability distributions. So we will first consider discrete distributions, since whatever we have been doing so far have discrete outcomes. So the classic distribution that we will encounter in physics is what is called a binomial distribution.